Hello, everyone. Welcome to the QuantUniversity guest series. We are already at the end, in the end of May, and I'm very pleased to invite today Satya Priya, who is joining in from California today, but he is a researcher at Harvard University, and he's been working on areas in explainable machine learning. And from one of his collaborators, Hima, who shared a paper recently on the disagreement problem in explainable machine learning. I thought we'd love to hear more about his research and what the work they've been working on in the context of explainable machine learning. And Satya was gracious to accept the invitation, and he'll be joining us today. As you all know, QuantUniversity has been hosting these workshops for more than 2 years now. So we have various themes on AI, machine learning, and primarily looking at themes of trustworthy machine learning and responsible machine learning, aspects of explainability, testing, fairness. These are all interesting themes, and we've been putting together various workshops and programs. And on QuantUniversity.com, you have a whole certification program available so that you can kind of enhance your knowledge base in these various emerging topics. In that realm, we are offering many more sessions this month. Next week, we are going to have an introductory session on aspects of machine learning testing. When you think about deploying a machine learning model, what kind of tests you need to think about. And then after that, we have two workshops. Agus Sugianto from Wells Fargo and team have released a new package called as PIML, which enables you to think about interpretable machine learning and also aspects of testing and outcome testing. So he's going to be joining in with folks from Wells Fargo to do a workshop on how do we think about testing machine learning models, how do we think about interpreting machine learning models. So we will have those two sessions on the 14th and the 21st. And we also have a workshop on stress testing machine learning models coming up on June the 27th. So we have a packed agenda for June, so we are looking forward to it. And I hope you can check out some of our offerings on www.quantuniversity.com so that you can see if there are any programs of interest you may be interested in joining the community. So with that said, I want to introduce Satya. Welcome, Satya. I'm just going to read a bit from your bio. Satya is a PhD student at Harvard University, working on trustworthy aspects of machine learning with Professor Hima Lakkaraju and Professor Finale Doshi-Velez. Before starting his PhD, he worked at Amazon Alexa on several responsible AI initiatives. He has published in various areas in algorithmic fairness, differential privacy, and machine learning explainability at prominent ML conferences such as ACL, FACT, EACL, CHI, and ICLR. Maybe we need an explainability, aspect to each one of these conference acronyms on what's focused on what. Postdoc are potentially interpretable acronyms, if you will. So Satya completed his master's from Carnegie Mellon University, Pittsburgh, where he worked on various smart conversational agents. And I believe he's doing something in this realm at his current role at Meta, where he's working on his internship. So welcome, Satya. Thanks for joining us. And I would love to kind of hear more about the work you've been doing. So the stage is all yours.
Thanks, Sri, for inviting, and thanks for the great introduction, and really happy to be here. And thanks everyone for joining in. So I'll be sharing my screen. Just a second. Sweet. So today I'll be going through a paper we recently published on which kind of proposes like this problem that exists in explainable machine learning, and we call it the disagreement problem. This was a joint work with amazing people at Harvard, MIT, CMU, and Drexel. And so I'll be starting off with some background on explainable ML and what specific thing we really care for in this area. And then I'll jump into the disagreement problem and go through the specifics of what analysis we have done and the conclusions that we make. So as we all know, that machine learning is everywhere in almost every application that require a lot of data, from autonomous vehicles, medical diagnosis, loan approvals, and many more. As it has grown in the past decade, we have seen that machine learning models have become a lot more better in making predictions and doing the tasks at hand. We have also seen that these models have become really complex. And with complexity here means the amount of data and the amount of parameters that go into learning the different patterns in the data is pretty huge. And this kind of brings up this question that how do these models really work? It has come to a point where we have this giant amount of deep learning models that go into production, but we don't really know how these predictions are made by these complicated models. And this is sort of is the basic question that the explainable ML tries to answer. And the setting is quite simple, where we have a black box model, which was trained on giant amounts of data and comprises of a lot of parameters and connections. And this goes through something like an explainer module, which ends up giving us a bunch of insights about why a prediction was made by these black box models. And it could be in varying representations. It could be either in the form of feature attributions, which essentially measures the importance of a feature in making a prediction. And then it could also be in the form of decision sets and all other variety of representations. Specifically, we'll be focusing on the feature attribution explanations, where essentially the explanation method is computing the scores, like the attribution scores of each of the features responsible in making a prediction. So before going to even the more complicated part, it's important to question, why do we really need interpretability? And there are several reasons, starting with the fairness issue, which basically where we basically try to answer whether a model has not learned something that we don't want it to learn. Like if there is a biased pattern in the data, we want to ensure that the model is immune to those problems in the data and it doesn't make any biased assumptions. Then we have causality reasons, where we would like to know what sort of properties or things that the model has learned about the natural world. And then we also look at the reliability factor, where we would like to know how well does the model really generalize. We know that the model has performed really well on a test set, but is it really generalizing, or can we really is the usability there or not? Which essentially brings this question of trust, where if you have a model that is complex and doing really well on the test set, would you be confident in putting it out to in production, for example, that scales up to thousands and thousands of customers? And then we have transparency, which is quite related, where we would like to know, if we are throwing in a model serving so many customers, we would like to know, what exactly is the model doing in the back end, and that would also help us in improving it or making it better as it goes. So I'll go through a couple of very basic algorithms that are out there that have found the space and have been quite useful in explaining some complicated machine learning models. One of the most popular ones is LIME, which essentially learns surrogate or linear approximation of model in some local neighborhood. So if you look at this image, this is quite a complicated decision boundary that the model has learned. But if you look at a local space, it seems like it's linearly separable data, and LIME essentially learns a linear model around it and gives out explanations based on that, given that linear models are easily interpretable and helps in giving us the insight in the local space. And then we have a bunch of gradient-based methods, which basically, the one that we saw before is more model agnostic approach, where it doesn't really, it doesn't have to give too much details about the model, but just give the inferences, and LIME is able to learn a model, a simpler model out of it. Whereas in gradient-based methods, it's a model-dependent approach, where we give it the model, and it basically, using the gradients, it gives out explanations of what really model found important in the input in making a prediction. So a couple of examples are shown here, where we have an image classification application, where given image of a bird, for example, the model predicts what bird it is. And these are the different maps that are generated by the different gradient-based explanation methods. You can see that a basic gradient doesn't really give much, but as you make some improvements over it, like smooth grad, which essentially aggregates gradient across different inputs generated with with some noise sampling. And as we see that some of them do really well, like you have, backprop doing really well here. And so there has been a lot of advancement in this space, and we have reached to a point where we can see some good explanations getting generated. So if there is any question until then, this is basically like a very high level overview of where we are, and I can move on to the next section. But if there are any questions, I'm happy to take it.
Yeah. So Satya, let's go through. I know you have a lot of slides. I'm going to be keeping. I'll be watching the questions. So if there are any, I'll either stop or we can hold off the questions till then.
Sounds good. Thank you. Okay, cool. So then we can go to the specific problem that we proposed in this paper. I'll essentially divided this into 3 sections. One is the explaining the whole problem, and then going into the depths of the quantitative study and the qualitative study related to it. So intuitively, the problem is with this setting where we have this complicated model that we're trying to explain, and the explanation here is basically telling us which feature is more important in making a decision. And the problem arises when a practitioner uses one explanation method, let's say LIME, and gets some explanation. And this is for a simple task where we are using this bunch of features to predict, let's say, a diagnosis, to basically diagnose a problem. And let's say for some disease, explanation method 1 says that is the heart rate and fever that the model took into consideration in making a diagnosis. Whereas, when we run it over another explanation method, it gives out a completely different story. And from a practitioner point of view, this is quite of a complicated situation where it doesn't really know which method to pick or what exactly, what insight to take from here. And this is what we call as the disagreement problem, where the explanations generated by 2 different methods for the same model prediction is completely different. Which we expect it to be having more agreement and give more cohesive insight out of it. So our paper basically addresses this problem of what exactly constitutes this disagreement between 2 explanations that is essentially explaining the same model prediction. And to start off, we set up some interviews. Since this is done from a practitioner's point of view, we set up some interviews with 25 data scientists working in technology and financial services and have been using explainability methods in their day-to-day use cases. And we basically sat with them and figured out what specific problems they face with the existing methods. And we had a pretty diverse crowd and experienced crowd with 16 of them having greater than 2 years of explainability experience, and most of them having at least a year. And all these data scientists have had experience with using some of the most common explanation methods. And with this survey, we got some great insights, great stats. One of them was that 72% of these participants found that the ordering that among the top features returned by these explanations are different. And what that means is, if let's say LIME says that feature A is most important, most contributing feature in making a prediction, SHAP says that it's feature B. And there's this ordering difference that exists in these explanations. Similarly, people noticed that 76% of the participants noticed that the direction of top feature contributions is different. And what it means is, when we get attributions or explanations, some feature might positively contribute to a prediction, whereas some would negatively contribute. And what was seen by most practitioners was that if LIME says that feature A is positively impacting the decision, the other method, SHAP, disagreed with it and suggested that it actually negatively contributed to the prediction. So there was this level of disagreement, which is quite significant when you think about it. And this was observed by 76% of the participants. We also saw that in a lot of cases, 84% of the participants, in fact, noticed that the set of top features were in fact very different. And what that means is that if there is top K features returned by Lime, that set was completely different, which was returned by SHAP or any other method. So that's another way of, that's another way of suggesting that there's a disagreement. And then following it up with something more, we saw that majority also saw that there was a difference in relative ordering. So this was like it gives a pretty clear picture that practitioners, majority of them see a huge gap or disagreement in between different methods, and that leads to a lot of problems. And we'll see in the follow-up slides how this impacts. Just to note that we don't make any comparison in absolute terms of the feature importance values, because essentially they're not really comparable as they are being generated with optimizing different functions, different losses, and that it's not essentially like comparable. So the thing that we look at is if feature A is more important than B, that should ideally stick around with different explanation methods as well, and not their specific feature importance values. Just a note. So based on the survey, we formulated 6 metric, which measures disagreement quantitatively. With the first one being the most simpler one, which is essentially measuring how much is there an overlap between the top features that were returned by explanation method 1 against the second one. So the more the overlap between these top features, the higher is the agreement. And the lower this overlap, the higher is the disagreement. And similarly, we made it more stringent by adding rank agreement as well. So we don't, in this metric, we don't just care about the overlap, but we also care about how these features were actually ranked. And then we followed up with addressing the issue that we found in the survey about direction by using a sign agreement metric, which is essentially saying how much of the common features have the same sign in attribution. And then we combined the signed and ranked to basically give another metric which considered not just sign but also ranks and sign. So these are like the 4 metrics that were based on, that was a function of K. So you can test it over different K values, and K here mean that if you want to test it over the top 1 feature, top 2 feature, or some top K. So this is the 4 metric based on that. And then we also had 2 other metric, which is not dependent on K, but instead was on the entire set. One of them is rank correlation, which is essentially a Spearman rank correlation between the 2 ranks of features that were returned by 2 explanation methods. And then we had pairwise rank agreement, which is not just taking the rank correlation, like unlike an rank correlation, it's essentially checking how much is the relative ordering the same or similar in the 2 set of explanations. So these were the 6 metric that we proposed that quantitatively measure disagreement between 2 explanations. So using these metric, we went on and analyzed how much do these metrics actually capture the underlying disagreement between different explanations on real-world data sets. And for that, we tested we basically going through the analysis on all the 3 data modalities. For tabular, we used the very popular Compass and German credit. And the black box model here was with increasing complexity from as simple as logistic regression to gradient-based, gradient boosted tree, random forest, and feed-forward neural network. For vision, we took ImageNet, which is a very popular image classification data set. And we used, for black box model, we used the ResNet 18. And then for text, we use the LSTM simple encoding architecture, with AG News being like a popular text classification data set. And for explanation methods, we basically analyze disagreement between these 6 explanation methods. The first 2, Lime and kernel trap, are model agnostic, perturbation-based explanation methods, where the rest 4 are more gradient-based approach. So these are 6 really common, very popular explanation methods that are used in current literature. So just to give a quick summary here, like COMPASS is basically this data set that is popularly used in fairness cases, which predicts the risk for recidivism. We have German credit, which is also very similar, which is also used for fairness experiments and predict the loan applicant's credit. And then we have ImageNet, which I'm sure like a lot of people would have heard from the deep learning community, that this is like a popular object recognition data set, and AGNews being like a pretty common text classification data set, which predicts the topic given a sentence. So for tabular data set, going through some results, we noticed that the disagreement, as you can see here, this is computing pairwise signed rank agreement, which is basically telling how much is, like each box here is telling how much is the attribution from grad is agreeing with Lime, and also how much is, it's basically giving you a pairwise agreement. And we noticed that for a lot of cases here, the agreement is pretty low. For a lot of cases, it's in fact 0. And we see some agreements as well. Like for example, for smooth grad and grad, we see some higher agreements, and we have detailed some of the intuition behind it. But overall, the picture is quite clear that there is a strong disagreement between the different explanation methods when we see it from the metric that we have proposed. And just to give a broad sense, we see such pattern in almost every metric. Feature agreement, fortunately, giving better results, giving more agreements, given that it was just computing the overlap. And as we go to the different metric, more complicated ones, we see that things get, this disagreement continuously increase. And the takeaway here is that these metrics have been able to capture some of these disagreements and can give a pretty good picture about how much these disagreements really vary and quantify them. So just to go through some insights, so we see that as K increases, which is the top K feature that we are analyzing, as we increase K, we see that the rand agreement decreases, which was quite intuitive to understand as well, because if you increase the top K features, you are asking the 2 models to agree even more, even though they were disagreeing for even lesser K. So as K increases, the disagreement goes worse as well. We see some agreements, reason being that there are similarities in how they are computed. For example, gradient is a simple gradient on one image, whereas smooth grad is an aggregation over different images. So there is some similarity, and that's why we see some agreements there. But we also see significant disagreements, like gradient and integrated gradients, which kind of presents this dichotomy among gradient-based methods itself. We also see these patterns in other data sets and other models as well, and I would encourage to look at the more detailed results in the paper. And the other more important factor was, so for tabular data set, we analyzed this disagreement for different model types, from neural networks to linear models to decision trees. And we noticed that as the complexity of the model increases, the disagreement gets even worse. Which is kind of makes the situation worse, because essentially you're using explanation methods to explain more complex models. So if it's disagreeing more on complex models, then it's not really serving the purpose. And we saw similar results for text data as well, and we actually saw a worse result here, where the disagreement was even more clear and was even a lot lower than what we saw in tabular. So it also suggests that for a larger input dimensional space, we see this disagreement getting a lot worse as well, which kind of relates to the earlier argument that disagreement getting worse with complex models. So these were, and we saw similar results for input for image case as well. And the takeaway from these results was that we have like these disagreement metrics. One has been able to capture the underlying disagreements well, and the disagreements that it has captured is quite severe in most cases. And this is kind of a huge problem in explanation methods. So yeah, just to give a quick insight or text data here as well, that the rank agreement and sign agreement often was under 0.1. So basically, this is suggesting that less than 10% of the times the explanations actually had any level of agreement, and for more than 90%, there wasn't much. And yeah, the pairs of gradient-based explanations showed a little bit better correlation and agreement compared to gradient and the model agnostic approaches or perturbation-based approaches. We also saw that Lime, like I should go back here. So Lime, so this is basically the result where we have rank correlation between the two explanations generated by two methods. And we noticed that these correlations were higher when we compare Lime with the rest of the gradient-based approaches compared to that for kernel SHAP with the others. So this is just another observation that we made. And there are a bunch, for the interest of time, I'm not going through all of them, but these are just some of the things that we noticed. And you can see here that gradient-based method among themselves have higher correlations than the rest. So this was a positive sign, but yeah, this is just another pattern to take into note. So based on this quantitative study, we went into doing another level of survey, or we were curious how practitioners really solve this problem. If this really exists and it's that major, then what are the different ways people have been solving it, and what is the underlying set of rules or understanding that people have to get out of this problem, essentially. And for that, the question that we were trying to answer in the last leg of our analysis was, do interpretability practitioners experience, and how do they really resolve these things in a day-to-day workflow? And in the setup, we basically did a survey where we invited practitioners who are familiar with Compass risk prediction setup, and we showed them basically pairs of explanations, and I'll show the apparatus in the next slide. But essentially, we showed them these prompts of different explanations and from different explanation methods, and asked them whether they really see a disagreement or not. And we asked them follow-up questions as to whether they were, how they were able to solve it given that situation. And then we collected a bunch of their comments and thoughts, and did some analysis and brought some insights that I'll present in the next slides. So this was the setup, where we basically gave some detail about the data that was used for training the model, and that was used to train the black box model. And we gave them the description of the different explanation methods. And then we gave them these prompts, which is essentially the two explanations given by two different methods. One here in this example is Lime. The other one is gradient times input. And we basically gave them the feature attributions generated by these two methods. And with, of course, the sign and everything. And we asked them these two questions. One of them was, to what extent do you think the two explanations shown above disagree or agree? And we also asked, which of the explanations do they really rely on? Because it could be the case that, there are multiple philosophical discussions following this, but we wanted to know what practitioners think when they come to this situation, whether they have some grounds on behind choosing one explanation over the other, or is there something else that they take into consideration while choosing an explanation over the other? So with these, and this was basically the setup of how it looked like. And then we asked, posed this questionnaire about some of the things about, whether they are really familiar with explainability and some of these questions. And most importantly, the purpose of these questionnaire was to understand about how do they resolve such disagreements when it happens in a day-to-day workflow. And kind of get like their sense of understanding of these methods and how do they really tackle the disagreement problem. So we basically kind of summarized this whole set of outputs that we got from our survey in answering 4 questions. One is, do practitioners observe disagreements? And we quantitatively see how much percentage of people have seen it, have observed this, and in what severity. Then for our study, based on our study, we would like to know, are certain explanations favored over others? So when they come across this disagreement, whether they prefer one explanation over the other, or how do they really perceive this difference, was the second question that we wanted to answer. And the third one was, how do practitioners resolve disagreement, not just in our study where we have given some situations and some examples, but also how do they do that in their use cases and in their day-to-day operations. And with these, we got some great insights. One of them was that's for the first question, where we were asking, based on the prompts that we showed, what was like, whether they do see those disagreements or not. We noticed that 68% of the participants voted for mostly or completely disagree option, which is basically telling that 68% of the explanations essentially, the pair of explanations essentially were perceived as disagreement among the participants. And this shows that majority of the explanation pairs were in complete disagreement. And which followed up in the second question, where we were curious that if they are brought into that situation of disagreement, was there any specific pattern in whether a particular explanation is favored over the others. And we noticed that there isn't any great strong pattern, other than the fact that most of the users or participants chose SHAP on most of the occasions, and it was least for things like reading times input. And the comments that we got of why they chose that was quite interesting. Like some of them, or 36% of them, suggested that SHAP is better for tabular data. And the specific comment was that SHAP is more commonly used for tabular data. And 25% of them suggested that SHAP is something that they're more familiar with, and they believe that it has more information present and all of that. And then 14% is suggested that SHAP is a better algorithm overall. And the specific comments being that it seems more methodological, and SHAP is more rigorous approach in theory. So in a nutshell, what you can get from this is that there's no concrete way of picking one explanation when you get to the situation. And that was kind of the highlight of the study, that in these situations, the problem is there isn't much solution to it, essentially. Like, people are going with explanations that they find more familiar or easy, or where there is a lot of subjectivity involved in it, and it's important to get some concrete grounding on solving this issue. Which brings us to the third question, which is, how do practitioners resolve these disagreements? And based on our survey, the responses were categorized in these 3 choices that we found people mentioned. One method is inherently better than the other because of its associated theory, which 33% of the participants believed in. Then there were 32% who believed that one of the generated explanations matches the intuition better. So essentially, like, for example, the ones that you saw in the previous slide about SHAP, most people believe that SHAP gives, like, it has a better intuition in giving explanations over the other, so they went with SHAP. So that's what was the driving force for 32% of the participants in solving the disagreement. And then there were like 23%, which basically suggested that Lyman SHAP are better because Compass dataset is a tabular dataset, and it's Lyman SHAP is a better option there, which is something that they believed in. To look at some of the specific comments that we received on this, one of them being that some of the participants from category 1 basically said that there's no reason to believe that gradient holds anywhere other than very locally. Something is more rigorous based on the paper and axioms. There are some suggested that gradient explanations are more unstable. And we found similar comments. We got some great comments on the second one as well, where people gave their opinion that seems unlikely that all features contributed to a positive classification. Features such as prior count or length of stay are important. So they're essentially, what they're trying to do is they're looking at the features and making sense of whether it maps to their intuition or not. And if the explanation maps to their intuition, then they're selecting it, else they're rejecting the explanation. So this is what essentially is the nutshell of these comments. So we have collected all these comments, and which kind of supports the argument. For the third, another category where people were going for more Lyman SHAP because of the Compass data being a tabular data, and most of the analysis that's out there in the papers are on Compass dataset, which is tabular. So people believe that it's better for tabular dataset, and that's why they moved on with Lyman SHAP as their top choices. So these were some of the kind of decisions, kind of reasons of why they chose a particular explanation method when they were brought into the situation of disagreements. And then we wanted to know that other than this study that we have done, which was quite specific on Compass data, we would like to know how do they see it in other cases, in the cases that they observe, and what are basically the different factors do they use in resolving such disagreements. And at a broad survey, we realized that 50% of the participants suggested that they're making arbitrary decisions. So they're not really, there's no theory or any specific guidelines as to whether one explanation is better than the other or should be chosen or the other that they can use. And some of them, were completely unsure as to sometimes, like, they were not even sure if there's like a resolution to it, and they end up not really resolving it. So it's about 86% of the survey participants essentially said that the decisions, there is literally no good way of resolving this disagreement, which kind of supports our claim as well that this is a problem that is quite severe in its case. And yeah, sure. I mean, for different for each of these different options that we had presented, we had like a bunch of comments that we got in each of them. Like one of them was for making arbitrary decisions. We had like such disagreements are resolved by data scientists picking their favorite algorithm. I try to use rules of thumb based on results in research papers and or easy to understand outputs. Essentially, it's kind of suggesting and enforcing the same things we had in the previous slides, where participants are essentially looking at their intuition and their understanding of the explanation methods and making decisions based on their subjectivity about the explanation methods, and which is kind of a problem because we would like to have more concrete set of guidelines or theory that suggest whether one explanation is important or is correct over the other, and if there is a way to really resolve this problem. And yeah, there were some more comments, which is like, there's no clear answer to me. I hope research community can provide some guidance. So these are all some of the comments that we got that supports our claim on that side. So moving to the last part, as we get closer to the time, is about the limitations and future work. So specifically, as we looked at in the presentation, we have framed the problem in quantitative sense as to what is a disagreement problem, how do we measure it. I did some quantitative analysis on some of the real world data sets in all three data modalities and found egregious level of disagreements, which kind of puts in the problem at a much higher priority. And then we did some qualitative analysis where we did some user study that says that basically suggests that there is no way that is available right now to solve this problem, and the problem is severe and it does exist, and it does put the practitioners in a difficult spot in getting insight about the model. And just to reiterate some of the things we found, 84% of the interview participants reported encountering the disagreement problem in their day-to-day workflow, and 86% of participants indicated that ML practitioner employed arbitrary heuristics or just did not know how to resolve the problem, which brings us to the follow-up works that we can think about. Some of them being that why does these issues arise, which is an important question, as to we would like to know what factors in these methods that kind of brings these disagreements or different explanations. There are arguments that are out there, like some of them being that they are telling different explanations, they are telling different things about a prediction, which is right. But essentially, we would like to know what specific things are they saying differently among each other. If Lime is giving a different explanation than SHAP, then there should be some idea as to what exactly does the Lime emphasize more and SHAP doesn't, and vice versa. So these are some of the things that needs to go down into more grounded theory. And we would like to have some, principled evaluation metric to distinguish reliable explanations from unreliable ones. And the kind of idea here is that if there are two explanations that are completely different, can we say that one of them is not right and the other one is right, or vice versa? And there is nothing that really gives us a clarity on that. And which brings us to this question that, should be, it's important to rethink some of the explanation methods that are out there, that are they really serving the purpose of explaining, or is there something fundamentally not working that's causing this problem? So yeah, in summary, explanation methods disagree, and practitioners essentially have not much clue as to how to resolve this. And the follow-up is to, think about solving it and how we can make it more reliable and more usable from a practitioner's point of view. So yeah, this was the talk. Thank you for listening, and I'm happy to take any questions or any discussions.
Well, thank you, Satya. This was very enlightening. I'm so glad that you were able to talk to practitioners and get their insights. I mean, one common theme I hear, not just from practitioners, but anybody coming new into the whole explainability world, is it's too complex. I mean, people are kind of still understanding what data they are working with, what is the context in which they are actually building these models, where will it be used, the choice of the metrics, the choice of first figuring out whether these models actually work for intended use, whatever is the use case. In addition to that, we are adding this whole new layer of explainability. And I mean, you come from a world wherein you have a list of conferences you go to, you interact with the researchers who are all probably very comfortable with the terminologies and the verbiage. But many practitioners I work with have absolutely no clue. And even explaining the formulations is not going to help them. So how do we bridge that gap? I mean, the practitioners gave so many answers, but I'm pretty sure many of them are either coming from a community. You mentioned in the sampling of the practitioners, you spoke to the data scientists, but the data scientists are typically not there in abundance. The qualified data scientists are not there in abundance. So they may even not even have clue of what they are even trying to interpret. They may be just going with a cookie cutter. I reference this score, which meant this. Can I apply the same kind of an interpretation with my score, right?
Yeah.
So how do we go from here? I mean, every conference I see more approaches, more metrics. What's going wrong in here?
Yeah, this is a $1 million question. Yeah, absolutely. I think the thing here that is missing is explanation. Means kind of different things. It's a very ambiguous term in some sense when we try to ground it. And when I see papers, I see them, say that, oh, here is another explanation, and then there is another explanation, but they don't go into the depth of what they really call an explanation. And it's a great question because it kind of confuses different people who are expecting something else with the word explanation, but they go into this approach and they end up getting into this problem of disagreement, and they're not understanding what it's giving. So it's definitely a very valid question, and I think there's a lot of discussions that I see on these, and I think my personal opinion is that I think there is a need for a special attention on how we define it at one to some strong or concrete terms, and also to make sure that we communicate that well in the papers, that instead of just calling it an explanation, we should instead go with defining it and mentioning that this is the use case that it's applicable to, and here are some of the ways where it's not useful, essentially. And so that guideline I feel like is missing, and definitely it's something that would help as we that's one of the steps I see that could help in doing that, because it's good to have no explanation rather than incorrect or ununderstandable explanations. So it's I feel like it could be the right direction to make that clear in the paper, that where it's applicable and where it isn't. And hopefully that will help.
In a similar realm, Satya, is there an agreement on what is what in not from researchers? I mean, there is ambiguity in terms of what means what, but even from a practitioner's perspective, is there even an agreement on what means? I mean, we're talking about disagreement, but is there even an agreement that I am understanding this and I can vouch that this is what I mean and this is what the metric is saying me, so that I can actually do my work as a practitioner? I gotta do work, right? I won't be just happy with proving something and moving on, right? So what do you think is happening there?
Yeah, it's a good question. I mean, my impression has been that practitioners, because I was a practitioner before joining my PhD, I was working for Amazon, so I was doing some of these. My understanding has been that what I would want to know is what a model looked at, or what a model thought was important, or what was the thing that it put more weight on. And it could differ a lot. For example, if somebody is not doing machine learning at all, like it doesn't have the background for machine learning, then that could become even more complex. But someone who has some clue about like how machine learning algorithms work, I see an algorithm as putting some weights on these features and then giving out some prediction, essentially a weighted combination, and giving out some number. So this is a very it's hard to say for everyone, but I feel like that is something that is there, that few practitioners do think that it's essentially what we want to know is what features are really causing the problem. For example, for debugging cases, which is a very popular case for explainability, where you have this ginormous model and it makes a very weird prediction. We would like to know what feature or what was there in that input that prompted the model to do this. So it's very much varied across different use cases, but this is one of the ones that I was kind of like used to work on. But this is like, yeah, this is just, I think it depends a lot on the use cases. And so far I have seen that this approach of kind of like attributing importance over these features is something that does have some level of consensus, even though may not be for a majority. But
interesting. And how do you think, in the context of the various methods out there, why shouldn't we just stick with interpretable models? Because if ultimately I am going to be trading complexity versus all these other assumptions we need to make, why can't we stick with building that theory and focus on those kinds of models wherein we can at least agree that we are seeing the same thing?
Yeah, there is actually a lot of work by Professor Cynthia Rudin who argues for essentially having interpretable models, and it makes sense. I mean, we should definitely, wherever we can, we should have that. The problem of having inherently interpretable models is that they're not that expressive. So if the task is really complex, as face recognition or something that requires processing a ton of data and a ton of features, these simple models are not that expressive to learn that complex decision boundary. And that's one of the reasons why we actually went with, and kept going with very heavy parametric models. And so that's like the trade-off. And that's what some people call it, like the interpretability, complexity or accuracy trade-off in some sense. So it's, I completely agree that wherever we can use an interpretable model, and if it's giving us the required performance, then for sure we should definitely go ahead with it. And of course, in future we would like to make models interpretable so that we don't run into issues of having another model kind of giving explanations and running into problems. So.
And also, just a thought in here. I mean, like you mentioned, from a sampling perspective, from your the people who answered your surveys. I mean, like I work with, as you know, many of my audience are in the financial services industry, and typically there is a structure because there's a culture of risk. There is also legislation and regulatory aspects in the financial services industry. So you have like formal model risk management groups, right? So who may or may not be involved in the design of the algorithm, but they are going to be asking the tough questions, both in terms of, what was the due diligence done, and also running different kinds of tests, trying to understand, potentially explain. There are also legislations coming out saying, well, you cannot just, say that, okay, my large language model gave this as an output, so that's the reason why we are giving you this particular answer, kind of a thing, right? So we should be giving specifics to our end users if they get denied for credit, or if their transaction was marked as fraudulent, or whatever it is. So in those cases wherein just having the global explainability metrics would not suffice, you got to kind of think about local. So where is the effort in kind of getting all the researchers together and saying, look guys, we got to have these people in mind when we are building these, and build out a rule book or some effort to think about the end users who are going to be taking these decisions, model-driven decisions, as not super comfortable with all these technological innovations which are happening in the conference space in the research world. Where do you think we should be focusing our efforts in kind of getting the chasm narrowed, if you will, or bridging that gap?
Yes, if I understood your question, we are basically, what you're asking is, we are giving some very like the representation of an explanation may not be very easily understood to someone who's 2 level or 3 level up the ladder, which I do feel like is another problem, which I don't see a lot of, because I think we are still struggling in some sense with trying to get some very basic and more technical, in some sense, explanations that we can then, give a different representation to. Although there are some explanations that are quite easily understandable. Like, for example, counterfactual explanation is one set of explanations that basically gives out a pretty intuitive way of explaining a decision, where it kind of tinkers with some of the features and values. And you can ask questions like, if my salary was higher than some value, then what would the prediction of the model be? And that would give you some insight about what model is really thinking. So there are some representations that are out there that are helpful. Decision trees, people find them quite easy to understand as well. So that's there. And then there are some, I guess, like, there are some of these approaches, but yeah, you're right. I mean, there isn't a lot of work that is translating it to something that is more understandable by someone who's not too much into technical, but instead it's more on the but yeah, this is great. These are great questions. I think we're getting there, and I feel like these problems and these kind of feedbacks to the community would definitely, like, there's a lot of discussions on these things happening. So I'm quite optimistic that this would get better.
Yeah, hopefully so. I mean, like, this is all amazing research, Satya, and I'm so glad that you're asking the questions to the practitioners. And I would love to see, I mean, like, is that something you could make anonymously available, like the full results, like all the whole answers? I mean, not to kind of decipher like what the intent was, just to get a feel for what the answers were. Is that something the data could be released?
I think in our paper we have mentioned, we have put up almost most of the comments that we got. Most of the comments that were kind of like that were kind of like giving us some insight, other than some of the not very informative ones. But yeah, feel free to take a look, and if there is something specific there, I'm happy to.
Yeah, I mean, I took a cursory look at it, and two things which I feel could be maybe when you do a part 2 of this kind of survey. One is domain specificity, because a healthcare problem is not the same as a military application or a financial application. So making sure that you're kind of focusing on a specific domain, because that means, I mean, in the financial services world, you cannot have real good ground truth on anything. I mean, because things keep changing. So having the domain specificity. And the second one is the users you mentioned, basically, having a distribution of users, kind of having through the model developers, the model testers, the end model users, and also the people who are going to be affected by the model, right? So, what in case I use Lime and give you an explanation versus I use Shep and give you an explanation, what will an end user interpret it as? And what level of, basically looking at, various facets of explainability, but also thinking about, the pros and cons of giving, maybe even doing an A/B test, saying if you are only given interpretable models and you are expected to answer questions, versus you now have all the tools available, post-hoc explainability tools for another cohort, and then looking at their interpretation. Do you think there is going to be a disagreement problem in the cohort who are only given interpretable options? And would they be more comfortable, and would they also be more confident in making decisions? So I think those would potentially help, at least understanding the distribution of potential people who are going to be using these, given the various tools and facets in a constrained setting. What would their interpretations be? And potentially summarizing those, we could even see the maturity of maybe the financial community of practitioners versus a healthcare community of practitioners, versus maybe even someone who is building autonomous vehicles and constantly dabbling with computer vision problems, but having a team of 1,000 computer scientists kind of working on this problem, kind of thing. So it could potentially give at least spread out that numbers so that you will be able to focus on, well, this particular cohort probably needs more, or should even be advised not to touch something that they don't understand.
Yeah, no, these are all great points. I think domain specificity is definitely something yeah, it's definitely great, great idea. And yeah, I totally agree that these applications are different and the responses could vary a lot based on that. So yeah, this definitely makes sense. And yeah, I would definitely be happy to follow up on this. These are great ideas. I've noted that down.
Awesome. Yeah, thank you so much again, Satya. I hope you enjoy your California stay before coming back to Boston. And I'd love to get a cup of coffee or lunch with you when back in Boston. And we will continue these weekly series. Next week, we'll have a briefing on the state of the art on machine learning testing, again, Tuesday at 12 o'clock. And I hope to see you there. And as I mentioned, we are going to be releasing details about the workshops we're going to have with Dr. Raghu Sujianto from Wells Fargo on the 14th and the 21st in the next few days. So if you're not signed up, please do sign up on www.quantuniversity.com so that you get these updates. And I hope you have a wonderful rest of the week, and we will see you soon. Thank you so much.